Welcome to Grade 9, where learning becomes an exciting adventure. Watch until the end to understand every textbook concept clearly. Like, comment, and subscribe for daily lessons. Visit rehanstudio.com for new syllabus practice questions, revision resources, and exam preparation. Lighter oil floats, denser water sinks. So we drain the water first.
Ready to go beyond. Crude petroleum is separated into fractions using fractional distillation. How does a refinery do it? By fractional distillation, splitting crude oil into different fractions. Ready to go beyond. Fractional distillation separates components with small boiling point differences, less than 25 degrees Celsius. This method handles liquids whose boiling points are close together, less than 25 degrees apart, where ordinary distillation struggles. Ready to go beyond. The gaseous fraction is compressed into steel cylinders, where it liquefies and is used as LPG. The gas fraction gets compressed into steel cylinders, where it becomes liquid. That is, the LPG in your kitchen. Paper chromatography. A water drop on sketch pen writing spreads the color, and black ink may split into several colors. Drop water on sketch pen writing and the color spreads, and black ink often splits into several colors. Surprised? Activity 5.5. Take a 3 cm strip of chromatographic or filter paper and draw a pencil line 2 cm from the bottom. Take a 3 cm strip of chromatography paper and draw a pencil line 2 cm from the bottom. Activity 5.5. Mark a spot with a black sketch pen at the center of the line. Put a dot of black sketch pen ink right in the middle of that pencil line. Activity 5.5. Put a thin layer of water at the bottom of a gas jar, measuring cylinder, or beaker. Pour a thin layer of water at the bottom of a gas jar, measuring cylinder, or beaker. Activity 5.5. Dip the strip vertically so its lower end is in water, with the water level below the ink spot. Dip the strip vertically so its lower end is in the water, but keep the water level below the ink dot. Don't drown the ink. Activity 5.5. Observe as water rises through the paper. The ink separates into different color spots. Watch. As water climbs up the paper, the ink separates into different color spots. Magic? No, science. Paper chromatography. Paper chromatography separates mixture components using differences in how they interact with the solvent and the paper. Paper chromatography separates the parts of a mixture using their different attraction to the solvent and to the paper. Paper chromatography. The liquid carries substances up the paper, separating them by how fast they move. The rising liquid carries the substances up. Those that travel faster end up higher. That is how they separate. Activity 5.5. You can also try green food color with a 2% mass by volume salt solution as the solvent. Try a variation. Green food color with a 2% salt solution as the solvent. Activity 5.5. You can separate pigments from spinach leaves or flower petals. Some cases need alcohol or a solvent mixture. You can even separate pigments from spinach leaves or flower petals, though sometimes you will need alcohol or a mix of solvents. Threads of curiosity. Chromatography is from the Greek chroma, meaning color, plus graphene, meaning to write. So it means writing with color. Word origin fun. Chromatography comes from Greek chroma, color, plus graphene, to write. Writing with color. Fitting name, right? Pause and ponder. True or false? Salt can be separated from a salt solution by evaporation or distillation. Think. Yes, both remove the water, so this one is true. Pause and ponder. True or false? Distillation can separate two liquids even when they have the same boiling point. Think. If they boil together, can we really separate them? So this one is false. Pause and ponder. True or false? In paper chromatography, the solvent level should be above the sample spot at the beginning. Recall portion 148. The solvent must stay below the spot. So this one is false. Pause and ponder. True or false? Evaporation and crystallization are the same process. Careful. One just removes the solvent, the other grows pure crystals. So this one is false. Methods of separation. Section 5.4 covers separating the components of heterogeneous mixtures. Now section 5.4. Separating heterogeneous mixtures. Different tricks for different mixtures. Separation of two immiscible liquids. Oil and water form separate layers and do not mix. They are immiscible liquids. Pour oil and water together and they refuse to mix. They sit in separate layers. Such liquids are called immiscible. Separation of two immiscible liquids. Sand and water, and iron filings and sulfur are also heterogeneous mixtures. Sand water and iron filings mixed with sulfur are also heterogeneous mixtures. Keep collecting examples. Activity 5.6. Pour 5 milliliters of mustard oil and 20 milliliters of water into a 50 milliliter separating funnel. Pour 5 milliliters mustard oil and 20 milliliters water into a 50 milliliter separating funnel. Activity 5.6. Let it stand undisturbed. Two layers form, yellow mustard oil on top and water below because oil is less dense. Let it stand quietly. Two layers appear, yellow mustard oil floating on top, water sitting below. Oil is lighter, so it floats. Activity 5.6. Open the stopcock slowly to collect the lower water layer. Close it when the water is almost drained. Slowly open the stopcock, the tap, to let the lower water layer run out. Close it just as the water is nearly gone. Activity 5.6. Collect and discard the small middle portion that may contain both liquids. That tiny middle bit that has both liquids mixed, collect it separately and discard it. Don't spoil your pure samples. Activity 5.6. Open the stopcock again to collect the oil layer separately. Now open the stopcock again and collect the oil layer on its own. Clean separation done. Brain teaser. What if two immiscible liquids of the same density are mixed? How will the layers form? If two immiscible liquids had the same density, how would the layers form then? Tricky, isn't it? Gases as mixtures. Gases mix easily and uniformly, so most gas mixtures are homogeneous, like hydrogen and oxygen rocket fuel. Gases mix easily and evenly, so most gas mixtures are homogeneous, like the hydrogen and oxygen mix used as rocket fuel. Gases as mixtures. Smoke, fog, and dust in air are heterogeneous mixtures with a gas as one component. But smoke, fog, and dust in the air are heterogeneous mixtures. Here a gas is one of the components. Solid-solid mixtures. Most solid-solid mixtures are heterogeneous. Use a property of one solid to separate them, such as a magnet for iron nails from sawdust. Most solid-solid mixtures are heterogeneous. Trick. Use a special property of one solid to separate it, like using a magnet to pull iron nails out of sawdust. Alloys. Examples include brass, about 80% copper and 20% zinc, bronze, about 80% copper and 20% tin, and stainless steel, iron with carbon, chromium, nickel, and molybdenum. Examples. Brass is copper and zinc, bronze is copper and tin, and stainless steel is iron with carbon, chromium, nickel, and molybdenum. Suspensions. A suspension is a heterogeneous mixture where solid particles don't dissolve but remain suspended throughout the medium. A suspension is a heterogeneous mixture where solid particles don't dissolve but float around throughout the liquid. Suspensions. Suspension particles are larger than solution particles and are visible to the naked eye. These particles are bigger than in a solution, big enough to see with your naked eye. Suspensions. Examples include sawdust in water and tea leaves in water. Examples. Sawdust in water, tea leaves in water. Chalk water from Activity 5.1 was 1-2. Suspensions. Filtering muddy water removes some particles, but the water often stays cloudy. Filtration isn't always enough. Filtering muddy water removes some particles, but the water often stays cloudy, so plain filtration isn't always enough. Suspensions. For very fine particles, we use centrifugation and coagulation. For very fine particles, we need better methods. Centrifugation and coagulation. Let us learn both. Centrifugation. Centrifugation spins a mixture in a tube at high speed. Centrifugation spins the mixture in a tube at very high speed. Round and round, fast. Centrifugation. The centrifugal or outward force pushes heavier particles outward to settle at the bottom, leaving lighter liquid on top. The outward force flings the heavier particles to the bottom, leaving the lighter liquid on top. Centrifugation. It is used in labs to separate blood components, red blood cells, and plasma, and in many chemical industries. It is used in labs to separate blood into red cells and plasma, and in many chemical industries. Threads of curiosity. The spinning game is called Fugati in Marathi and Kikli in Punjabi. That spinning game you play, Fugati in Marathi, Kikli in Punjabi, works on the same idea. Centrifugation. A paperfuge is a low-cost, hand-powered centrifuge that helps detect malaria and anemia in remote areas. A paperfuge is a cheap, hand-powered centrifuge that helps detect malaria and anemia in far-off villages with no electricity. Brilliant, low-cost science. Activity 5.8. Make a centrifuge model with a cardboard disc and thick thread to see heavier particles move outward. Build a model centrifuge from a cardboard disc and strong thread and watch heavier particles move outward. Coagulation. Adding powdered alum, fitkari, to muddy water makes fine suspended particles clump together. Add powdered alum, fitkari, to muddy water, and the tiny floating particles clump together into bigger lumps. Coagulation. Alum is a white crystalline substance used in water purification. It acts as a coagulant. Alum is a white crystalline substance used to purify water. We call it a coagulant because it makes things clump. Coagulation. The clumps settle by gravity, called sedimentation, and can be separated by decantation or filtration. Those lumps then sink by gravity, sedimentation, and you separate them by decantation, pouring off, or filtration. Coagulation. Everyday coagulation. Making cheese, paneer, from milk using acid like lemon juice or vinegar as a coagulant. Everyday coagulation. Making paneer from milk by adding acid like lemon juice or vinegar. You have eaten coagulation. Colloids. Blood coagulates and its components can be centrifuged, yet blood cells aren't visible. So it is neither a solution nor a true suspension. Puzzle about blood. It can be coagulated and its parts centrifuged, yet its cells aren't visible to the eye. So it is neither a true solution nor a true suspension. Colloids. Blood is a colloid. Other colloids include milk, tomato sauce, and ice cream. Blood is a colloid. Other colloids you know: milk, tomato sauce, and ice cream. Tasty examples. Colloids. Donated blood is separated into plasma, platelets, and white and red blood cells and stored in blood banks. Donated blood is separated into plasma, platelets, and white and red blood cells, then stored in blood banks to save lives. Colloids. Solutions, suspensions, and colloids differ mainly in the size of their particles. So the real difference between solutions, suspensions, and colloids comes down to one thing: particle size. Colloids. Solution particles are the smallest, less than 1 nanometer. Colloids are 1 to 1,000 nanometers. And suspensions are greater than 1,000 nanometers. Sizes to remember. Solution particles are tiniest, less than 1 nanometer. Colloids are in between, 1 to 1,000 nanometers. Suspensions are largest, greater than 1,000 nanometers. Colloids. Unlike suspensions, colloid particles don't settle and stay uniformly dispersed, like in a solution. Unlike suspensions, colloid particles don't settle down. They stay spread out evenly, looking uniform like a solution. Sneaky. Tyndall effect. Recall activity 5.1. The light's path was not visible in solution A. Remember activity 5.1? In beaker A, the salt solution, the laser's path was not visible. Hold that thought. Tyndall effect. Particles in suspension B scattered the beam, making its path visible. But in beaker B, the suspension, the particles scattered the light so you could see the beam's path shining through. Tyndall effect. In mixture C, the light's path was visible too, though the mixture looked homogeneous. And in beaker C, the milk mixture, the path was visible too, even though the mixture looked perfectly uniform. Interesting clue about colloids. Tyndall effect. The Tyndall effect is the scattering of light by particles, explained by the scientist John Tyndall. This scattering of light by particles has a name. The Tyndall effect, explained by the scientist John Tyndall. Tyndall effect. For example, a light beam entering a dark room through a small hole is visible due to scattering by dust and smoke. Everyday example. A beam of light entering a dark room through a small hole becomes visible because dust and smoke particles scatter it. Remember portion 8 sunlight through leaves? Same thing. Tyndall effect. Another example. Floodlights in a sports stadium show the Tyndall effect. Another. The floodlights at a sports stadium show the Tyndall effect beautifully at night. Tyndall effect. Scattering occurs in a colloid or a suspension, but not in a transparent solution. Remember the rule. Scattering happens in a colloid or a suspension, but not in a clear, transparent solution. Tyndall effect. A colloid has two components, the dispersed phase, the solute-like particles, and the dispersion medium, in which they are suspended. A colloid has two parts, the dispersed phase, the solute-like particles, and the dispersion medium, the substance they float in. New pair of words. Note them. Emulsions. Emulsions are colloids where both the dispersed phase and the dispersion medium are liquids. Emulsions are a special colloid where both the dispersed phase and the dispersion medium are liquids. Emulsions. Oil-water emulsions are either oil in water, like milk and vanishing cream, or water in oil, like butter, body lotion, and cold cream. Two kinds of oil-water emulsions. Oil in water, like milk and vanishing cream, and water in oil, like butter, body lotion, and cold cream. Look around your home. Emulsions. Some medicines are made as emulsions to disperse them in water, make them palatable, and reduce greasiness. Some medicines are made as emulsions to spread evenly in water, taste better, and feel less greasy. Emulsions. Emulsifying agents stabilize emulsions, for example, the proteins in milk and butter. To keep an emulsion from separating, we add an emulsifying agent, like the proteins in milk and butter. It is the peacemaker holding the two liquids together. Emulsions. Make an emulsion by shaking a few drops of cooking oil with water containing a few drops of soap solution. Try it. Shake a few drops of cooking oil with water that has a few drops of soap solution, and you will make your own emulsion. Pause and ponder. What type of mixture are clouds, tiny water droplets, or ice crystals in air, and why? Think. Clouds are tiny water droplets or ice crystals floating in air. What type of mixture are they, and why? Hint. Particles floating in a gas. Pause and ponder. Why do cities with lots of smoke and dust in the air often look hazy? Think. Why do cities full of smoke and dust often look hazy? Connected to scattering, the Tyndall effect. Activity 5.9. Complete Table 5.1, comparing solution, suspension, and colloid across nature, particle size, visibility, filtration, settling, and the Tyndall effect. Complete Table 5.1, comparing solution, suspension, and colloid across nature, particle size, visibility, filtration, settling, and the Tyndall effect. Great revision exercise. Closing ideas. Separation isn't always simple. For example, you can't easily separate all the ingredients in lemonade once mixed. A gentle reality. Separation isn't always easy. Once you make lemonade, can you take back the exact sugar, salt, and lemon? Not so simple. Closing ideas. Separation happens in nature and in our bodies too. The kidneys remove waste from blood. Separation also happens inside nature and inside you. Your kidneys separate waste from your blood every second. Amazing, isn't it? Closing ideas. Big challenges include removing plastic waste from oceans and rivers and treating sewage using sedimentation, coagulation, and filtration. Big real-world challenges. Removing plastic waste from oceans and rivers and treating sewage using sedimentation, coagulation, and filtration. All things we just learned. Closing ideas. Segregate waste at home. Dry waste like plastic, paper, glass, and metal can be recycled. Wet waste can be composted. Your homework for life. Segregate waste at home. Dry waste like plastic, paper, glass, and metal can be recycled. Wet waste can be composted. Separation helps the planet. Closing ideas. Researchers work on recovering valuable materials like lithium from old batteries in phones and laptops. And finally, scientists are working to recover precious materials like lithium from old phone and laptop batteries. So this chapter you just finished? It is shaping the future. Well done, class. You made it through all 223 portions.
And that brings us to the end of this part. Well done, dear students. You have taken one big step in understanding mixtures and their separate, so don't miss it. If you enjoyed this lesson and it helped you, please subscribe, like this video, drop a comment, and share with your friends who are also studying. Keep learning, stay curious, and I'll see you in the next part. Hello, class. class! Today we begin Chapter 5, Exploring Mixtures and Their Separation. Mixtures are everywhere, in food, drinks, medicines, factories, nature, and even inside our bodies. In this chapter, we will discover how mixtures are formed, how they behave, and how science helps us separate them. Look closely. The white sugar you enjoy every day begins its journey as green sugary juice. To get those clean, sparkling sugar crystals, we carefully separate the unwanted materials step by step. This separation science, working quietly in the real world, from a huge factory all the way to your dining table. Welcome to Grade 9, where learning becomes an exciting adventure. Watch until the end to understand every textbook concept clearly. Like, comment, and subscribe for daily lessons. Visit RihanStudio.com for new syllabus practice questions, revision resources, and exam preparation. Here's something truly amazing. Doctors can detect diseases like malaria using only a few drops of blood. How? By carefully separating and studying the different parts of the blood. Just look at how powerful separation can be. It doesn't only help in factories and kitchens, it helps save human lives every single day.
Dilute. As ingredients, it's misconcentrated. Same ingredients, different strength, that's concentration.
3 simple ways to measure how much solvent is hidden inside a solution. Mass M volume percent, tilde meng MV percent, and going mass percent. MV percent means is hidden inside a solution. 3 simple ways to measure how much solvent is hidden inside a solution. Mass, the volume percent, volumed incleus for volumed, a first, and a volume per volume mushier in salient. Keep adding sugar, and eventually, no more will dissolve. That's a saturated solution. Heat helps solid dissolve, but it drives gases out. During Zebvinnerfreit, si sforsio entisent, the stunned, it drives gases a scout. As it cools, pure crystals grow. This is crystallation.
Boil the liquid, then cool the vapor back down. That's distillation.
When boiling points are close, a tall column splits crude oil into petrol, diesel, and kerosene. Wanting to be no iperosomes, solcutins ter ferding, forn of light ter rackagation. Watch closely. Black ink is secretly a rainbow. Lighter oil floats, denser water sinks, so we drain the water first. Some solids turn straight to vapor, sublimation.
Iron is magnetic, so we just pull it out.
Oil and water refuse to mix, so how do we split them? Deeper water sinks, lighter oil floats on top. Open the tap and let the water out first. 2 pure liquids, separated simply by density. Can a solid skip liquid and turn straight into vapor? Camphor turns directly into vapor when heated. It resolidifies above, leaving the sand behind. No liquid stage at all. That is subduration.
Iron is magnetic, so a simple magnet magnet becomes easy.
12 metals mixed into one dozy. Bronze evaporate the by salt temperature.
This trick uses a property only one of them has. Iron is magnetic, sawdust is not. So a simple magnet lifts the iron away. Find a unique property, and separation becomes easy. Welcome to Grade 9, where every lesson becomes a journey through time. See every concept come alive before your eyes. Stay until the end and master every chapter with confidence. Like, comment, and subscribe for daily learning. Visit rihanstudio.com for new syllabus practice questions and complete exam preparation.
And that brings us to the end of this part. Well done, dear students. You have taken one big step in understanding mixtures and their separate, so don't miss it. If you enjoyed this lesson and it helped you, please subscribe, like this video, drop a comment and share with your friends who are also studying. Keep learning, stay curious, and I'll see you in the next part. Allah Hafiz and take care.